So we have these new derivative rules, but I want to remind you that we can interpret the derivative exactly the same way that we have when we were just using the power rule. The derivative still tells us the rate of change, and the derivative can still tell us the slope of the tangent line. So in our last example for this section, we're going to use our new derivative rules, but then interpret the derivative and remember, oh yeah, this is what it tells us. So in example 4, it says the estimated resale value R of a car after t years is given by the function R of t equals 22,000 times 0.88 raised to the t power. Part A is asking me to find R prime of t and R prime of 2. Here we have an exponential function where the base is 0.88, so we might want to have the derivative rule for exponential functions written down in front of us. From our last video, if we had y equals b to the x power, the derivative of that function is y prime equals b to the x power times the natural log of my base, which is b. So when I go to find the derivative of r of t, I want to find r prime of t. Well, first, I've got this 22,000. Well, that 22,000 is a constant multiple. I'm multiplying by 22,000. This is not 22,000 plus 0.88 to the t power. So that means that I am just going to multiply whatever my derivative is by that 22,000. It's just going to come down to the next step. So that's the first factor. Then I need to talk about the derivative of 0.88 raised to the t. And here's where we're using that new derivative rule. So the derivative of that part should look like 0.88 raised to the t power times the natural log of my base, and in this case my base is 0.88. So here is my derivative. First of all, there's not much I can really do to simplify it. R prime of t is 22,000 times 0.88 to the t power times the natural log of 0.88. This problem also asks me to find r prime of 2. So I'm going to take 2, I'm going to plug that into my function for, I'm going to plug that into my derivative for t. So r prime of 2 is equal to 22,000 times 0.88 to the second power, or squared, times the natural log of 0.88. Here we will probably want to have our calculators help us out, get a decimal approximation. I ended up with negative 2,177.87. I'm going to round to 2 decimal places since we're most likely talking about dollars and cents. So r prime of 2 is negative 2,177.87. So okay, we've got our derivative, we've got our r prime of 2. Part B is going to ask me, is the car's value increasing or decreasing after 2 years, and how can you tell? So these words, increasing or decreasing, really are asking me, how is the car's value changing? In other words, what is the rate of change? And this says after 2 years, so okay, after 2 years, that means that t is equal to 2. So that means I want to look at r prime of 2. Well, we did that already. We did that in part A. We said that was negative $2,177.87. So if I want to interpret my derivative at t equals 2 years, I can look at this, and really what I'm looking at is my result positive or is it negative? Because if it's positive, I have a positive rate of change, which would mean my car's value is increasing. If it's negative, that would mean I have a negative rate of change, which would mean my car's value is decreasing. So in this case, I can say the value is decreasing, And I can even be more specific here than just to say it's decreasing. I can say it's decreasing by, in this case, $2,177.87 per, well, what was my unit of time? Here, this was per year. So per year. And as far as, well, how can you tell? Well, we could tell just by looking at the sign of r prime of 2. We can tell because r prime of 2 is negative. So even though we've got these new derivative rules and we'll be using these new derivative rules, remember that the derivative still tells you the rate of change, and it can still tell us the slope of the tangent line. So we just want to keep that in mind as we work with these new and different functions, because we'll learn more derivative rules in the next section and in section 3.4. But the derivative still tells us the same pieces of information. It still tells us the slope of the tangent line, and it still tells us the rate of change of our function.